origins of life. We're looking at how habitable planets form and how life might evolve on those planets. And our very first guest as a WiCOR speaker is Professor Sara Seager from MIT. Sara is really well known in the field of exoplanets and has been an inspiration for me for a long time, and so we're absolutely thrilled to have her here. I have a really long list of things that Sara has done and awards that she's won. I will hit a few highlights. She was the Deputy Science Director of the TESS Observatory, which is one of the ones that looks for new exoplanets. She won a MacArthur Award. She's a member of the U.S. National Academy of Sciences, and most recently she won the 2004 Kavli Prize in Astrophysics. And so we are absolutely thrilled to have Sara with us here tonight to tell you about the search for habitable worlds elsewhere in the universe. So with that, I will turn it over to Sara, and thank you all for coming.
Thanks. So the story for the search for life beyond Earth actually begins here on Earth, but it begins billions of years ago, when a simple single-celled bacteria, cyanobacteria, figured out something very clever. I don't know about you, but I don't think of bacteria as being very clever, like that slime in your fridge. Or I don't know, maybe it is clever because it grows pretty quickly. But it turns out that this life form figured out something very clever, how to harness energy from the environment. That's photosynthesis. And in the process, generated a waste gas, oxygen. So you know how we all need oxygen, right, to survive? But believe it or not, without plants today and photosynthetic bacteria, we would have virtually no oxygen in our atmosphere because it's so reactive. It shouldn't be there at all. That's like if you open the perfume bottle and the smell kind of makes it across the room, you'll smell it. But if I close that bottle, soon it'll go away because the molecules will react. So we're thinking that our Earth is like a beacon because we have this gas that shouldn't be there. And it's so reactive, it has to be continually replenished. So when I look at the night sky and the other stars, I love to imagine there's an intelligent alien civilization on a planet orbiting a nearby star. And they have the kind of telescopes we're hoping to build, and they look back at our Earth. And they're going to suspect there's life here. So it's not from like big structures like the Great Wall of China. It's not from like pollution or city lights, but it's from oxygen, a gas that doesn't belong. So that's kind of where we're at. We really are thinking like we want to find a gas on another planet that doesn't belong. And there's kind of, I'm going to try to unpack this whole story for you and just try to share with you where we are in this whole search. But to start with, and just to make sure we're on the same page here, because there are some kids here, and you probably already know this, but I'm just going to repeat it just in case you forgot. That is like every star out there is the sun. And if our sun has planets like Mercury, Venus, Earth, Mars, then it makes sense, right, that other stars have planets also. And they do. And we astronomers, including actually students in this room, have found planets out there. So many planets. It's like nearly every star has planets. There are thousands of planets we know about, but there are literally trillions and trillions of planets out there. So for today, I'm going to answer the questions I get asked most often. And these are questions from students. They're like the people I meet at the dog park. They're scientists and journalists, and these are the questions. I'm going to go through them. Now, while I'm going through these questions, I want you to think about what's the most popular question I get, okay? Because there's one question on here that is like so popular compared to all the other questions, and I'll get asked it, oh, even after I finish answering the questions, people will still ask about it. So you might be able to figure it out. So the first question is, what is an exoplanet? And you know, to answer that, I wanted to share these. How many people have seen these NASA posters? NASA made these like retro posters, like imagining if we could go there. Kepler 186f, where the grass is always redder on the other side. There are a lot of planets around small stars, and the small stars give off little energy, and they're very red. So the artist is just kind of making this up, but I'm just trying to capture some of the flavor of our imagination about exoplanets, and here showing that the vegetation is red instead of green. Experience the gravity of HG40307G, a super-Earth. And here it's imagining another, well, it is actually another planet where the surface gravity is higher than here on Earth, so they're imagining you going to that planet and parachuting and just thinking about that one. Relax on Kepler 16b, the land of two suns, where your shadow always has company. This is a planet orbiting two stars. It's a binary star system where there's two stars orbiting each other, and the planet is orbiting these stars. That's why I always like to say sometimes science fiction got it right. A planet with two suns. Well, of course, there are just so many planets, there's really no way to capture them all for you, even in a 1-hour talk, even in like a semester-long class. Well, you don't have to understand this to understand the rest of the talk, but just so you can graphically get a tiny glimpse of, actually it was just a fraction of the planets we know about. But just to center you here, what the message I'm trying to get across is how many planets there are and how diverse they are. This is showing you planet mass in Earth masses. And this is showing you orbital period, like how long it takes the planet to go around the star in days. But for your purposes, and again, I'm just speaking to the graphically inclined here, so if you don't understand graphs, you can ignore this, but this is a log-log plot. This is like, 1, 10, 100, 1,000, spanning decades in like mass, and spanning literally days to hundreds to tens of thousands of years. So planets come in all masses, all sizes, or all orbits. And we really do want to, try to capture this. It's kind of crazy because we were looking for a solar system initially, and it turns out our solar system with like Mercury, Venus, Earth, Mars near the sun, and Jupiter, Saturn like far from the sun. Guess how many true solar system copies we have found out of those thousands of planets? Kind of zero, actually. And it turns out our system, it might not be like super rare, it's just really hard to find. But we think that something like less than 10% or smaller of sun-like stars have a solar system. Instead, they'll have like a Jupiter where an Earth should be. They have some planets that are so close to the star that we think the surface is like melted rock. And some of these planets go orbit their star so quickly that their 1 year, the time to complete an orbit, is literally less than 1 day. So all the systems out there are pretty crazy. But here, we're trying to talk about we'll get there in a second. Let me just conclude this part of the talk. What is an exoplanet? It's just a planet that orbits a star other than the sun. We know of thousands of them, actually, and we expect that nearly every star has a planetary system. So a lot of you knew that already. That was just warm-up. We have exoplanets. There are a lot of them out there. This is a question people love. When and how will we find another Earth? Well, it turns out, our Earth, it's not like an Earth is so hard to find. It would not be, say, fainter than the faintest galaxies ever studied by Hubble or the James Webb Space Telescope. It's not like our Earth is intrinsically dim. The problem is an Earth like ours is right next to a star, and that star is overwhelming. It turns out that our sun, thinking of the Earth-Sun twin, is so big. Our Earth is tiny. Our Earth is 100 times smaller than our sun. Our Earth is 300,000 times less massive. Our Earth is 10 billion times fainter. If you were going to, let me ask you this for a moment. I don't know how many decimal places you're used to working on. Like, let's imagine you're going to build a deck on your house or on someone's house. And you've got to measure out the planks to, let's say, they've got to be like 20 feet long. Are you going to get a plank that's 20.0 feet? Would it be 20.000? Would it be 20 followed by 9 or 10 zeros? Like, let me put it this way. If you were going to drop everything now, or you were going to embark on a undergraduate research project, which method of finding another Earth would you want to work with? Would you want to work with one that goes where it's about planet size? So now it's area, so you're going to 4 decimal places. Okay? Who would want to do one that involves mass? So now you're going to kind of 5 or 6 decimal places. We're thinking of remember the deck, and you never would measure, in your everyday life, how often do you go to that? Who would do the 1 in 10 billion? Guess which one's my favorite? Oh, we got one, yeah. Okay, yes, the NASA person is, 1 in 10 billion. Let's do it. Well, I don't know. There's this kind of thing in life, right? And I don't know where you're at, all of you, or undergrad. Sometimes you feel like harder is better. I don't know if you're in that group, or if you're like, well, I may as well do the easiest thing. I mean, it's really hard to say, right? Because sometimes you feel like there's more reward for doing the harder thing. But on the other hand, you just want to get the job done. Well, if anyone voted for the first one, that's where we're at now, actually. We're doing the easiest one. It's planet area, and we're typically the biggest game in town, but not the only one, but it is transits. It's about planet size. And here, the way we search for planets and are going to study them is, this is the most common way planets are found today. Planet goes in front of the star as seen from our telescope. Now, on the top there, what you're seeing is a cartoon, because we don't have any stars spatially resolved other than our sun. What we do measure as astronomers is the bottom, where we measure the brightness of a star as a function of time. And when the planet goes in front of the star, it drops by a very characteristic brightness. Actually, it's pi r squared of the planet area over pi r squared of the star. So the drop in brightness is related to the area ratio. If you know the size of the star, you can back out the size of the planet. We're going to come back to this in a moment, but for now, I did want to tell you a tiny bit about how we're going to find planets, and then you're all going to participate in like a mini planet finding exercise here.
I have a question. So
Sure.
Are you keeping any like indications of the parameters of the star you're looking for, or are you just looking at any star?
Good question. We're typically looking for stars like our sun or smaller, but our surveys that I'm going to tell you about is any star. We're looking at millions of stars. Whatever falls in our field of view is technically fair game. But if the star is really big, we'll never find a planet because that drop in brightness is too small. So it's kind of any star, but we have our favorite ones that we're really going after. So here is, we're going to talk about the MIT-led NASA mission TESS, like the girl's name Tess, Transiting Exoplanet Survey Satellite. It launched in 2018 out of Cape Canaveral. And maybe someone else here was at that launch. Yeah, Thomas, yeah. Cool, yeah, that was pretty exciting because like we worked on this for a really long time, and everything and like so much money and time is just in the little tippy top of that ginormous rocket. And it was an amazing rocket. It was that, see how it's like looks almost fake bright? It was super, super, super bright. But what's inside there at the very top is ultimately the little space telescope. It's about like this big, kind of this tall, this wide. And what is in it are these 4 cameras. They're like a specialized telephoto lens, basically. And these folks here are putting it together here on Earth in the laboratory. And there are covers on top of these telescopes that came off before it launched. And they have to wear this bunny suit because you don't want like your hair or skin cells like contaminating. You know how your glasses or like your camera can get really dirty? You don't want to do that. So everyone has to be all dressed in this bunny suit. And here is the radio antenna that communicated to Earth. These are the solar panels. Inside here is kind of everything else, the batteries, the computer, the data handling unit, and things like that. Here's a picture of the lens. Actually, the lenses are only like this big. They're only 10 centimeters across. There are these giant baffles to block out stray light. And you see how it's so cool the baffles are ribbed? Because you don't want the light bouncing in and then bouncing to your detector. You want it to bounce in and bounce back out. Yeah, so here's kind of a picture of what it looked like in the lab. And here's an artist's conception, an illustration of like what TESS does. So inside, TESS is orbiting Earth, and it has these 4 cameras bolted to the platform. And each camera is looking at quite a big part of the sky, a 24 by 24 degree square. But the cameras are lined up in a way that they make a giant strip on the sky. So this kind of answers your question, because in that strip of the sky, there are kind of 20,000 stars of interest, but there are literally 1 million stars that are being monitored. And this strip of the sky is monitored for about a month at a time before TESS will go and it will tile the sky. It does 1 hemisphere per year, basically. Now, I just want to I know that there's probably who here is working on TESS data? There are actually some students. Yeah, look, if you look around the room for a second, it's like not zero. It's like maybe half a dozen people are actually working on this. Well, TESS has been operational for a while. There's a lot I could tell you about it. But you know the constellation Orion? It would fit in one of the squares. So how we find data. I'm going to compress like 10 years of work into a single slide. And everyone, I want you to look here and see if there's someone you know, because there is someone in this audience in this picture. But what the TESS mission does is we see all these stars. In that picture, that's a real image from the TESS camera, but that's a tiny fraction of 1 camera. And what TESS does is that the computer does most of the work for us. It finds the star, it identifies the star from a catalog. It basically measures the brightness of the star in an image, and it does that image after image after image. And this computer, it's kind of like not doing all your homework, and someone had to figure this out. That's what took 10 years. And then it figures out which ones have a little drop in brightness out of all these tens of thousands or even millions of stars. And then it has to know, is that drop in brightness like a planet, or is it like something else? But at the end of the day, we actually do have humans involved. We call them vetters, like V-E-T-T-E-R-S. And Lizu, why don't you just raise your hand so everyone can see in the picture? Lizu was an undergrad at MIT. Can you see him in the picture? He's there in the picture. And this was like our original group that we worked hard, because basically at the end of the day, I don't know, maybe you trust computers fully to choose all the planet candidates. No, okay, you don't trust it. We have the humans we have a lot of auxiliary data, and we make a call. Is this worthy of planet status or planet candidate status? And if it is worthy, we put it on a list. It goes out to the community of astronomers all around the world who try to follow it up. But enough of that. We're going to try it being a vetter here, all of us together. We're going to try to be a test vetter so you can get a feel for these planet light curves. So it's a little complicated, but I'm just going to briefly explain what we're going to be looking for. On the top here, you're seeing the brightness of a star over the course of about a month, actually. And these dots here, this is relative brightness. This is time in days. It's kind of an arbitrary scale. Sometimes the spacecraft wasn't working or it was downlinking data. But basically, we're going to focus on the bottom plot, which is complicated to explain, but it comes from the top plot. It's just this, we call it phase-folded data. But you're looking here at the black are the data, the blue are average data. And what we're looking for is a transit. So we want to look for a very characteristic shape. And I gave you what we're looking for. So we're looking for a drop in brightness, a small drop in brightness. We're looking for what I call a box shape, because the planet goes across the star limb pretty quickly, then it's superimposed on the star, and nothing really happens till it's finished transiting. Then the star goes back to normal. Are you with me there? Okay. This flat, okay, box shape. Okay, this is what we're looking for. So one of the problems is that the biggest source of contamination are what we call binary stars. Two stars eclipse each other. That's the biggest contamination that we have. But in this case, you're typically getting one eclipse from each star. So you get like big, little, big, little. You're having odd, even, because these stars are both bright enough to cause, big enough, bright enough to cause drops in brightness from each other. And also, because they're so big with respect to each other, this one, in this picture here, it's what we call kind of grazing. It never really gets superimposed on the star because it's so big, it's biting off like a lot of that star continuously. Okay, that was a little bit of a crash course. I might not have explained it all well enough, but we're going to do this as a group. We're going to say the computer gave us a list of planets. Together, we're going to decide whether they're worth of getting a check, like are they a legit planet candidate or are they clearly not a planet. So here at the bottom, this is our brightness of the stars, a function of time. We're looking for a box shape. We're looking for a small drop in brightness. There's no units here, but it looks pretty big. We're looking for a flat bottom because the planet is small compared to the star and kind of just takes out a tiny bit. Anyone want to vote on this? Planet? Not planet? This was a binary star, and I kind of purposely tried to show you this shape so that you would see. Okay. I mean, admittedly now, these don't come to the vetters. These are thrown out by the computer right away, but I just wanted you to get a feel for it. And if you look at the top plot, those graphically inclined, what do you see here? Do you see how it's like odd, even, odd, even? They're all different. It's two different objects. It's not a planet going around a star. All right. Again, our job, we're pretending to be these human vetters. We got the data from the computer. We're looking for a planet transit box shape. Yeah, more or less. It's not a perfect world, okay? Small drop in brightness. Yeah, maybe. You can't really tell because we don't have a scale here, like a unit. Or actually, this one does. It's a few times 10 to the minus 3. Flat bottom light curve. Yeah, I mean, within those bounds. Okay, let's take a vote. Planet? Not planet? Okay, so far you guys are doing really well. This actually is a planet. And it's so spectacular because it's already a known planet. I want to say it's a Kepler planet, actually. I forget which one. But it was like a test. Like, could we recover a known planet already in the data? I know, it's a bit of a trick question, all of these. I mean, obviously they're handpicked to get a point across. But to you, this should be like, wow. From across the room, it's very clearly a beautiful, beautiful drop in brightness, very clear. Okay, let's take a look at this one. So we're looking at the bright blue dots, box shape. The blue dots we're looking at. Small drop, flat bottom. I mean, like, what is going on here? This red line, does it fit the data? You'd be like, either we're a really bad programmer or we just did something really wrong. We didn't, though. We're asking the computer to fit a transit, like a planet going in front of a star, given the data. And in this case, it's definitely not a good fit. And look at the top plot there. What's happening, this is a pretty crazy star. It's a variable star. It's pulsating. This is definitely not a planet. Now the computer will throw that out. We won't look at it. But I just wanted you to get to see what some stars are doing, what some light curves look like. Very variable. All right, we're moving on now to a slightly harder situation. We're looking at the bottom plot again, relative flux. There's no unit here, but we're looking for a box shape. Small drop in brightness. Flat bottom light curve. People are looking really puzzled here, but you know the small planets that are small and they're not the giant ones, the small ones that we want to find that might be able to host life, they're going to be really small, actually. And they're going to be like this, and the team has to face this. Do I call this a planet candidate and let all my colleagues around the world spend time following it up? Am I wasting their time? What should I do? I mean, we have a lot of extra information. We're not just staring at a graph, but I mean, let's put it this way. Do you want to be the one that doesn't put the planet that ends up being like an Earth? Sometimes I imagine there's these aliens out there and they're looking at their tests, you know, their equivalent light curves, and they're looking at our Earth, they're like, nah, that's just nothing. So yeah, what do you think about this one? Planet? Worthy of a planet, not planet, let's say, but worthy of a planet candidate. Would you upvote this? Okay, because we want to be generous, not upvote. Okay, well, we tended to be pretty generous, but we also have room for comments when we upvote these, so you'll know that, oh, it's probably nothing, but just in case. So we could do that. But in this case, I want you to see there is a tiny drop in brightness, but what's happening over here? See, there's a rise in brightness, kind of equivalent to the drop in brightness. So that's a big indication it's probably just nothing, probably just noise, just our instrument or the star itself. So yeah, you can give yourself a pat on the back if you were, I mean, you wouldn't have learned that from me. You had to have already known that before. You know, we don't have enough time here for me to teach you everything you need to know. But I did want you just to get this flavor of what the team actually is doing. All right, we've got one more. And by the way, those who know about data already, the computer's flagging like what it thinks are transits here, and then it's binning them all together to amplify the signal. Okay, we're looking for a box shape, small drop in brightness, flat bottom light curve. And remember what we saw before is it, yeah. Let's take a vote, planet. All right, you guys are pretty good. Yay. Yes, not only is this one a planet, it was one of our first planets we found with tests, and it was absolutely insane. Its year, the time it takes to go around the star, is 11 hours. And this planet actually likely has no atmosphere based on some follow-up data. And it turned out there's a lot of planets like this. Very short period orbits, very hot, probably no atmosphere. And it's just, yeah, one of many, many interesting planet archetypes out there. Okay, well done. So let's move on now, because remember that this part of the talk is about when will we find another Earth. And we're taking this easiest method of transits in planet area. But an Earth is really hard to find because our Earth-Sun twin is just a tough call. So on this, I've put a fake planet about the size of Earth compared to a real image of our sun. And that's a really tiny drop in brightness. So right now, we're not able to find Earths with the TESS mission. It's just too small, actually. And it turns out when eventually we want to study their atmospheres, that atmosphere is like the skin of an onion on an onion. It is just way too small for us. Now, am I allowed to assign homework here? Okay, just kidding. That's a joke. But we can actually work all this out. We're not going to do it here. I just want to say at the undergrad level, you can work out like the size of the planet compared to the size of the star from the light curve. You can predict and estimate like what the atmosphere signal is. We're not going to do that right now, but we're just going to take away with us that this Earth-Sun twin is not going to work for this method. It's just too small. The atmosphere is too small. The planet is too small. Instead, we're doing another kind of, I call this the Earth twin. We're going to go after Earth cousins. We're going to look for planets that transit small stars. Because see that's on the sun, and look at this one on the far side. This little dot here, it's the same size as this dot. And this is a cartoon of a real-size star, an M-dwarf star that's 1/10 the size of our sun. And doesn't it look so much bigger? Like it's going to block out way more light. It'll block out like 1% of the light, not 0.01%. The atmosphere is going to be really easy to see. So the whole field now, when we think of finding another Earth, it's not an Earth twin, it's what I call the Earth cousin. So let me take you on a little virtual trip to one of these like Earth cousins orbiting a red dwarf star. And this is an artist's conception. Definitely took the artist's license to make the clouds different color and the sky different color. But what's important here are a few things. One is these small dwarf stars, they give off very little energy. So for the planet to be the right temperature for life, it has to be pretty close to the star. This is the so-called campfire analogy. Small campfire, you got to huddle really close to that campfire to stay warm. So in some cases, it could be that that star is very big in the sky, actually, because the planet has to be so close to the star. Now, if you were my undergrad class, we could work that out. This star is way too big, actually, in the sky. But it could be. And the artist is also showing you like some moons, some other planets in the same system. But what's really interesting is that on these planets so close to the star, they're very close, that after some period of time, like tens of millions of years, they get into a low energy phase called tidally locked. They rotate one time for every time they orbit. That's what our moon does. It shows the same face to our Earth at all time. So it's one time every time it orbits. 1 day is equal to 1 year. But what this means is if we could go to this planet, is that the star or the sun would be in the same part of the sky at all times. So would you go to visit where it's always day? Well, you're at an astronomy talk, so you would want to visit where it's always night. You literally always have night. Or you could literally go where the sun is always setting. But they wouldn't call it sunset, right? Because it would just always be hovering like right there. It actually might be moving a bit, it turns out. I'm looking at the dynamicists. Once I did give this talk, and the people who work on like physics of orbits got angry, and they said it's not perfect like that. It actually will wobble a bit. But what's other interesting is that the closer a planet is to the star, the shorter it takes to go around. So 1 year on these could be equivalent to like 10 days or something. So if you're a kid in the audience, what this means is 1 year is about 10 days. Your birthday would be every 10 days. But I kind of feel like we'd be celebrating every century, right? Not every, because how would you have your birthday every 10 days? Like that would be crazy if you had to have a party every 10 days. But maybe it could be every 100 days. That's still like more often than we have here. So on second thought, maybe visiting these planets wouldn't be such a great idea because the stars have a lot of high energy. They give off flares and high energy particles. And you couldn't be glued to your phone because the high energy particles would knock out the electronics. It's like, what kind of sunscreen would you bring? And these flares, this is a real satellite picture of our own sun giving off what's called a coronal mass ejection. Part of our sun is coming off, perhaps associated with a flare. And yeah, I kind of think of it like, do you get snow days here? Like where you get so much snow, everyone's got to stay home? Yeah. Well, I always feel like on a planet like this, perhaps they have radiation days where they're getting a blast of radiation and they're told, look, you just have to stay down in your basement for a couple of days till this high energy gets dissipated. But I wanted to just tell you a story about our own planet Earth. And some of you may have heard of the Carrington event. In 1859, a kind of amateur/professional astronomer named Carrington in the UK was studying sunspots on our sun. And he noticed the sunspots brightened a little bit. And a day and a half later, our Earth became electrified. People could go outside, and by the northern lights, be able to read a book. They were so bright. And people saw northern lights almost down to the equator. And our sky was lit up for a couple of nights. And telegraph wires caught fire, some of them. And people found with the telegraphs they didn't need batteries. And what had happened was a part of our sun came off our sun, and we just happened to be in the line of fire. And people didn't know at the time because Maxwell's equations weren't yet articulated. But what happened was this part of our sun had a magnetic field embedded, and that magnetic field had our Earth's magnetic field and induced a current. So we didn't have a power grid back then. We do today, and I know it sounds like funny, but it's really not a funny picture. It's like a different kind of pandemic. And if you wanted to read about this, there's a really good fictional book called Aurora. And actually, this book, Aurora, you know how the disaster books, they have to have, like, something goes wrong that probably wouldn't? But in this case, it is about what happens to our power grid, and it's a fictional story. It follows two different characters. One's a prepper, one is like not organized in any way, and it follows them as in the aftermath. So that's the bad news, actually. But for these small stars, some of them have really big flares. Like this one star we really love called TRAPPIST. It had been observed for 80 days in a field of view by a space telescope called Kepler, and people saw 40 flares in 80 days. And one of those flares was estimated to be as energetic as our Carrington event. So imagine being on another one of these planets where you're getting blasted like constantly. Maybe the life is subsurface. Maybe it's extremely radiation tolerant. I don't know. I'm just trying to illustrate for you how very different these so-called Earth cousins are, the planets orbiting small stars. So how will we find another Earth? Well, we're going to fast track. So we're going to find Earth cousins instead of Earth twins. And we're also using transits, the most favorable planet finding technique. Okay, we're going to come back to the Earth twins soon, but I just wanted to leave that with you. Small stars, small planets, very different in terms of their environment. So the next question is, can we go there? Well, let's do some numbers here. I mean, the nearest star is really far, but let's do some numbers. If this is the size of our sun, how big do you think our Earth is? There's a clue there. It's about that size of that sunspot. I actually picked this picture out especially for you. Okay, if that is the size of our Earth and sun to scale, how far away would the Earth be? Yeah, it says, how far away would our Earth be? Does anyone want to take a guess? You can raise your hand or shout out a location on campus. Hawaii, okay. Well, if that's our Earth and our sun, actually, conveniently, our Earth is about 100 suns away from the sun, 100 sun diameters. So that wouldn't be in this room, but where would it be? Like down the block, let's say, okay. Well, if this is our star, this is what you're trying to answer. Where would the next star be to scale here? We can say Hawaii, yeah. I haven't worked this out, but yes, let's say Hawaii. I mean, it's far. There's lots and lots of space, and that is our nearest star. Our nearest star is 24 trillion miles away. Our fastest spacecraft would take a really long time to get there. Too far. Well, can we go there? Not yet. And just so you know, that's the question I get asked most often. Everyone wants to go. And one of the great things about exoplanets is, you know, back when I started working on this, it was so fringe, nobody would touch it, actually. And today it's so mainstream, there are thousands of people working on it. So I have this phrase I really like. I say in exoplanets, the line between mainstream and crazy is constantly shifting. So you know about how we can't go there? Well, people are thinking about how to go there. Not us people, but sending spacecraft. There's a name for this project. It's called Starshot. And the idea is to send up thousands of little tiny space chips. It's not spaceship, space chip. Maybe like about this big. And just like the little turtles when they're born, thousands of them are born, they don't all make it. But there's enough of them, so some hopefully will. And the idea is to send up thousands of these. They'll go launch to space, deploy solar sail, and we have to have a giant bank of like a square kilometer of lasers coherently energizing by photon pressure, accelerating these little chips. Well, they're big now because they have like a 2-meter solar sail to like a 20th the speed of light so that they could zoom by the nearest star system with planets, snap some photos, and send them back to Earth. Now, this project was given a big amount of money, like $100 million. It's not enough to get the project to work, but it's enough to shift that line. Because once we plant this idea that people are legit taking it seriously, it means that someday we hopefully can go there. Now let me ask you this. Let's say today we did have a way to get there, and we could travel at, let's say, 1/10 the speed of light, and the nearest star system's 4 light years away. So that would take about 40 years to get there, 40 years. I'm just curious about, and so if you think about what is about the right age to go, it's about age 20, right? Because you're an adult, and you could go, and then you get there, you'd be 60. I hope 60 doesn't sound too old, but because there's 60-year-olds here. But who would do that? Like, if you could literally volunteer to go, you're in your 20s. I know, right? And I'm sure there's more than one person. Like, you know, you'd go there, you'd have to be in that spacecraft for 40 years. But I forgot to mention it's a one-way trip. Maybe that was obvious. It's just one way. But you'd still go, right? I mean, there's always people who want to go. So I really believe in my heart someday we're going to find a way to get this job done. So the follow-up question, I'm going through the list of questions I get asked most often, is this is literally like, if we can't go there, why are we doing this? You know, we want to be able to go there. We're finding the planets. Well, if we can't go there, why look? Well, it turns out, you know, science fiction got a lot of things wrong. I don't know if there's any original Star Trek fans here, yeah? But Star Trek, you know, remember? They had to go travel at really high speeds to travel to the nearest star systems to look so that Spock, a favorite, right? He could use his planet analyzer and look at the surface. I mean, that's science fiction there, but our life as astronomers tends to be a lot more boring. We don't need to go there. We can use our telescopes. Like, we have the Hubble Space Telescope. We have our new James Webb Space Telescope. And so we're doing basically remote sensing. And so for the last part of my talk, I'm just going to give you some like updates of where we're at, because that's what we're doing, is we're studying the atmospheres. Remember oxygen? We're trying to look for gases that don't belong, and we really want to know what's out there. So I'm just going to give you like the summary of where we're at right now. Just so you know, what we're doing is we're looking at spectra. If you could take the rainbow and split it up into its constituent colors, you'd see that some lines are missing. There are some dark lines missing. Look at that. And each of those lines actually corresponds to an atom or a molecule, mostly in our sun's atmosphere, but some in our Earth's atmosphere. So every molecule has like a pattern where it removes gas, it absorbs starlight. And we really need spectra here because our own planets, Earth and Venus, they're about the same size and mass, but they're actually completely different. And through our planet finding technique like transit, unless we look at the atmosphere, we actually don't know what's going on. Venus is so hot, the surface is, at least the surface is too hot for life, but our own Earth is like this oasis for life. So the way we're doing this study right now, the kind of reason why the search for signs of life is getting a huge burst of energy is we feel like we have our first ever opportunity to look for signs of life in atmospheres of planets far away. And we're going to do this with the transit method. Remember we talked about that and you helped vet a few planets earlier in the talk. Here, what I want you to think about now, we're going to go a step further and think of the planet atmosphere. So if you see the cartoon on the top, there's the dark part of the planet creating the drop in brightness. But if a planet has an atmosphere, what happens? See how the planet looks a tiny bit bigger. It's very exaggerated here, okay? But the planet's a lot bigger with its atmosphere. So I want you to now take this and think about some wavelengths where the planet is strongly absorbing and other wavelengths the planet is not absorbing. So at wavelengths where the planet is strongly absorbing, or colors where it's strongly absorbing, the planet looks a tiny bit bigger. I'm going to explain that one more time, because if there's only one thing you could take away from the talk, I'd want it to be this. The planet area blocks the starlight, and we get a drop in brightness related to the planet area to the star area. But the atmosphere makes the planet bigger. So now the planet is bigger, and it's creating a bigger drop. It would create a bigger drop in brightness. So some wavelengths, the planet looks a tiny bit bigger than other wavelengths, and that is due to the effect of an atmosphere. And that's the main way we observe planet atmospheres today. That's the first way we're trying to find signs of life on other planets. Some of you have seen this already, but those who haven't, we're going to try to see a planet atmosphere. So what you're seeing here is the star. The black line is showing you the best fit to data at different wavelengths. And what you're seeing here is the star, it's normalized to 1, and the star drops in brightness because of the planet. But the different colors are different wavelengths. The W in the top corner is telling you what wavelength in microns, and the bottom is telling you the time. So your job now is to see if you can see one of the colors where it's dropping below the best fit line. There is a wavelength where the planet looks a tiny bit bigger than all the other wavelengths. Can everybody see it? So now I want you to just shout out if you can see it, what the wavelength is. You now have to coordinate. Here 4.5, I hear 4.3. Like, let's just let that land. You've all seen evidence for an exoplanet atmosphere. Like, this data is so precise with our new James Webb Space Telescope that we can literally just see this by eye. And it is like a huge triumph for us as an entire field of astronomy. Well, it's going to get a bit more technical here, so you don't have to understand this part to understand the rest of the talk. But what we do is we take each transit drop in brightness, and we ask, what is that drop in brightness? And we sort of reconfigure all of this to the amount of light blocked as a function of wavelength. So these white points are the data for each transit that we saw. The blue is just a model fit. And what you see here is what you were saying. You saw the planet looked a tiny bit bigger at wavelengths of 4.3, 4.4, 4.5 micron. And that's what you're seeing here. So to explain it a different way, it's the amount of light blocked as a function of wavelength. If there was no evidence of an atmosphere, this would just be a straight line. And I think you can all agree with me that this plot is different from a straight line. And that's our evidence for an exoplanet atmosphere. And what this gas happens to correspond to is carbon dioxide. It's a very strong feature of carbon dioxide at this wavelength where carbon dioxide is not like a really dominant gas in this particular planet, but kind of like a skunk spray, you only need a tiny amount to make a giant signal. So that's our giant planet, and we have, there's just a lot here. This is like an entire, really course in undergrad to unpack all of what this means. But here you see the amount of light blocked, and there's a lot of ups and downs. We're seeing a lot of different gases. Most of the planets we're studying now are giant planets. They're too hot for life. They have no surface as we know it. It's really hard. Okay, well, we're getting towards the end of my talk, but I do have something really complicated to tell you. And I just want to make sure everyone who's been able to follow along so far can have something a bit harder to mull over. And I remember we talked about how we can't find the Earth twin yet, but we have the small planet transiting the small star. And remember how we talked about the small star, they have flares and they have a lot of spots. This is like cutting edge current, biggest problem right now is these star spots. Because when our background star is not uniform, we have a really big problem. And it's a bit technical, but I just want to make sure that my astronomy colleagues can get something new out of this. And this is showing you now transit drop as a function of wavelengths. And you're seeing the ups and downs. Remember, the planet's supposed to look a little bit bigger at certain wavelengths. But if we imagine a planet with no atmosphere at all, but a star with a star spot, we're still going to get this up and down. Because it turns out that a star spot also looks different at different wavelengths. And now I want you to think of the size of the star. It's changing because there's a star spot. But if the star spot looks bigger or smaller at a different wavelength, the overall size of the background star will also look a different size at different wavelengths. Not all of you, it's a bit technical, and it's really just for my astronomy colleagues, but the thing is these stars, spots, they have their own spectra. They're not just a cooler star, and they're making their own up and down because the background star looks like it's changing size. And so when we have that contamination of the star and we match the planet atmosphere, we actually have this all jumbled up thing. And at the end of the day, this is our biggest hurdle right now to being able to see gases on the small planets transiting small stars. And that's kind of where we're at right now. Okay, well, transits are only the first part of a long story. It's a different talk to say we have tons of other telescopes coming up that will do the job we want. But just to summarize this part of the talk, if we can't go there, why look? We remote sensing with space telescopes to find and identify an Earth-like planet eventually and search for signs of life. So I'm now getting to the end of my talk. And I walked you through all the questions. I'm just going to summarize them now, and then we're going to have time for even more questions. So the questions I get asked most often, what is an exoplanet? It's a planet that orbits a star other than the sun. When will we find another Earth? Earth twins are off the table right now. We have this fast track to study small planets transiting small stars. Can we go there? Not for now. If we can't go there, why look? We have remote sensing. Now, I didn't tell you about that we found a gas that's a sign of life. I didn't give you a list of gases. I just told you about planets and where we're at. And that's because the story is unfinished. This story is part of your story. If you work on exoplanets, if you want to work on the signs of life, it is literally a generations-long search. So I hope that I've inspired you to learn more about exoplanets, to maybe be a part of the search one day. And let me just finish by wishing all of you clear skies. Thank you.
Thanks, Sarah. That was great. Let's see if this is on. It's not on. We may not get the questions on the recording. Oh, there we go. That helps. All right. So a few announcements before we take some questions. Unfortunately, our observatory is not functional tonight, and so we can't open it up and do sky viewing tonight. But once it's back up and running, it is open every Monday, the first and third Wednesdays of the month. And so please come and join us, and you can look on the webpage and see when that gets back up and running. And before you leave, if you're interested, we do have a few WiCOR t-shirts for sale. Come see Thomas. He's in the front row. So now we can take questions. If anybody in the audience has questions for Professor Seager, lots of hands went up. Uh-oh, my husband has questions. That's dangerous. All right, so we're going to start in the middle because I see students with their hands up. So we'll start there. You have to wait.
Can you go back to the place where you had the spot, the slide with the spot? I'm not exactly sure what happened there. So can you explain how so the next slide. So how did you add these data up? Did you so you looked for the data
Yeah,
off
this
the
is
spot
just simulate. By the way, this is just simulated data, so it's like fake data to make the illustration.
Yeah, so I want to know how would you do it? So you'd look for the data just off the spot and the data of the whole star,
right.
and then
Yeah.
you add them up?
No. I'm just trying to break it down for you. This is what we observe. It's all mixed together with the planet and the atmosphere. It's very hard to separate them because we actually don't know what is the contribution from the star spot. People are trying to figure that out.
So my question would be, now you'd get a specific amount of data, you'd have that, like that graph over there, and then you want to know exactly how much the spot contributed to this.
Yeah.
So how would you do that?
Okay, that is a good question, and there are like probably 300 people and entire PhDs trying to solve that. So I can tell you 3 ways. One way, we make models of stars with magnetic fields, and they're very complicated models, and we also shoot rays through the structure with all the right gases and molecules and atoms in the star and try to simulate what the spot would be. And then we figure out how many different, what is the spot configuration. That's one way. The second way is empirical. Sometimes a planet transits a star spot, and we can actually try to see what that spectrum is. But the best way, I got to tell you this brilliant idea a few independent groups had, and this one student and professor at JHU are running it. There's a system with more than one planet, and one planet appears to have no atmosphere. So we're going to measure the star when the planet with no atmosphere goes by, and the only contribution is due to the spot. And right after, the other planet will transit. And so we'll have like a kind of map of that star.
Yeah, but that's mainly dependent on having a planet that has no atmosphere.
Well, it would take a long time to unpack it all. There's evidence that that one planet has no atmosphere. And so, yeah, it does rely on that, yes.
Hi, I was wondering if you could go back to the slide where you were talking about how planets with atmospheres appear to be larger when they are in transit. So, like, say a planet without an atmosphere in that same moving across a star, how would you determine that it was just that big and didn't have an atmosphere as opposed to one that was smaller but appeared to be that large?
Can you ask that one more time?
Okay, so you're saying that as a star moves in front of the planet and it has an atmosphere, it appears bigger than it actually is, correct?
Yes, correct.
Okay. Now, say a planet that was just that, did not have an atmosphere, but it was that size on its
I see
own.
what you're saying, yeah.
How would you
it's
determine?
really many decimal places out. So this like change in size due to the planet atmosphere. It's really so tiny. So, we wouldn't really worry. We'll say our planet is like this big, and the atmosphere might add like a tiny, tiny fraction. So we could get it wrong, but it's not really, it's kind of in the noise, so to speak.
Okay, thank you.
What happens when after Tess makes the whole circle? What does it take recordings of
Good question.
after?
Yeah, the question is once Tess covers the whole sky, it does the northern sky and the southern sky, what happens? Well, so far, it's done it a few times. It just goes back and repeats its measurements again. And it's just trying to get more data so we can find longer period planets. However, after doing that a few times, it's actually kind of open to suggestions from the community. So if you had a really great idea, you could pass it along. I'm going to put Thomas on the hook, probably through Thomas, or Melinda, because, yeah, I mean, once it's done a few things a few times, it's looking for some new ideas. It's a bit constrained because the sun, the big baffle, like the sun and the moon can't get in the way. So it can't really just look anywhere, anytime. But after it's finished, it just keeps doing it over and over again until someone has a better idea.
Howdy. You said like the main problem with finding the Earth twins is because of the ratio of brightness from the large stars to the small. So could you not, or I'm maybe missing something simple here, but why couldn't you block out part of the outer radius of the large star to decrease that ratio in brightness?
Yes, okay. Well, the stars are point sources, so we can't just block out part of it. They're just literally points of light. It's just the cartoon that makes it look like that. Right. But there is a whole other method. By the way, I do an undergrad class in exoplanets. It takes the entire semester, even just to scratch the surface. So we'd literally talk about transits for 2 weeks, and later we can talk about another technique where we want to block out the starlight entirely. And then we're not relegated to just finding transits that are fortuitously aligned. We can find any planets. And we want to block out the starlight so we can see the planet directly. But remember, initially I was saying how Earth is 10 billion times fainter than our sun. So it becomes a much harder problem because we have to go to those 10 decimal places. But there are plans to do that. NASA has plans for the so-called Habitable Worlds Observatory. And it's actually very, very, very hard to do. It's an incredible challenge, and it's like a much later generation telescope. But if I can take that while we're getting another question, we want to block out the starlight so we could see planets directly. I'm going to tell you about my favorite project is about sending up a very special, ginormous screen to outer space that would block out the starlight so we can only see the planet light directly. It would have to be a very special shape because well, you can ask me about the special shape later if you care, but just bear with me for 1 second, okay? Because this is my favorite project of all time. It is called Starshade, and Starshade could launch with a telescope. It's a giant screen. The petals would unfurl from their stowed position, and this truss would expand and snap the petals into place. This Starshade is tens of meters in diameter. It would have its own spacecraft, and it would have to formation fly tens of thousands of kilometers from the telescope. It's like blocking out that starlight so you can see planets directly. And that is such a challenging task. The Habitable Worlds Observatory will have the equivalent of like a starshade, but inside the telescope. And a lot of time, effort, and money has gone on to thinking about how to do this problem, how to get the Earth twin. It's like a whole other chapter.
All right, who else has questions? I saw hands over here, and then we'll bring it back to this side. All right.
Yeah, I'm pretty sure I'm confusing science fiction with science right now. But the question is, because I think I just saw this on a National Geographic special. If we can figure out how to navigate a wormhole, I understood from this special that a wormhole could be a shortcut to the nearest solar system. So, question one, is this true? Question two, how much of a shortcut would it be to knock off 70,000 years?
Okay, so have you seen the movie Interstellar? No. Okay, go watch that movie, like this weekend, you're gonna love it. It's actually about that. There's actually, it's fictitious, but there's a wormhole like where Jupiter is, and they use this wormhole to go to three other planetary systems. And it's almost like what I was saying, like the planets are so far away, we don't know much about them, they have to get closer. It's a great movie. It's definitely, I bet you most people here, it's a fan favorite, yeah. Well, first of all, we don't know about any wormholes that exist yet. And the other problem is it would have such a strong gravity, it would rip us up like spaghetti. Like we would be dead before we got anywhere near that wormhole, unfortunately. And if they do exist, it would connect us to like another part of our universe, but it's almost weird. Like we might not even really know where. It might not really get us any closer. It might just take us somewhere else in our galaxy. So it is an idea we definitely love, but it's very impractical because we don't know of any wormholes and it would destroy us. But the movie is, you're gonna love it.
While I walk over there, I wonder if you have any advice for the younger generation beyond just the science and the technical stuff to do all these bold, amazing things that you do. Is there advice you'd give an earlier version of yourself of how to step into this space and do this kind of work?
Well, one of the advice is to find something you love doing that you're also good at. And that also pays the bills. So that's kind of the Venn diagram. But I think the best way, especially if you're an undergrad, is to talk to I got to put it back on you now, but the professors here, so we have several, you could just raise your hand, but you know, there can, lots of opportunities to take a class, try to get a project or summer internship, just kind of explore the space in which you can contribute somehow. But I think the bottom line is to learn how to program at some level because everything we do involves programming. So that would be my other more practical advice.
Did you have your hand up? Yeah.
What's the latest on phosphine in terms of something that potentially be detected
Phosphine, yeah.
in atmosphere?
Yeah, you know, I really had to think about which level of talk to give you, and I talked yesterday, like, to the astronomer, the professionals, so to speak, and I did tell them that. I'll tell you about phosphine. So in this whole search for gases that don't belong, we had a kind of preview of it with our very nearest sister planet, Venus. I was part of a team that reported a discovery of a gas that doesn't belong. It wasn't oxygen, although Venus does have the tiniest amount of oxygen that is completely unexplained. It was a gas called phosphine, which you might never have heard of. On Earth, phosphine is only associated with life. We make it as pesticides. It is sometimes made in industry. Life in, like bacteria in oxygen-free environment makes it. And when we put this out there, that we reported the discovery of phosphine in tiny amounts, but no known chemistry could make phosphine, we left some room without saying we definitely didn't think we found life on Venus, but we left room for signs of life. And this discovery was immediately incredibly controversial because in science we're very skeptical, and astronomers also, the data is all public, and people looked at the data, and a lot of people did not recover the signal. That's really bad news. But some astronomers did recover the signal. And it kind of has been going back and forth with the large majority not believing phosphine on Venus. But it really does underscore our own search for signs of life elsewhere. Because Venus is right next door, we do know a lot about it compared to exoplanets, but we're still not really sure what's going on. Yep.
Okay, I think we can take one more question, and then Professor Seager said she'll stay and talk afterwards for a little bit if people have more questions. All right, we'll go up here.
Hi, so I was wondering how and when did you first get into astronomy and what made you decide that that's a career that you wanted to pursue?
Okay, I always loved the stars since, I mean, how many of you have seen the dark night sky? Okay, if you haven't, you have to go see it. I'm sure there's somewhere not too far away where the sky is super dark and amazing. And I grew up in Toronto in the city, but I did get, when I was like 10, I got to go on a camping trip and I just, wow. But then later I learned you could be an astronomer for a job. But my dad said no, actually, because he wanted me to get a job where I could make money and support myself. I'm a parent now, and I have kids in college. And yeah, I mean, you don't want to be paying for your kid. You got to grow up. So I didn't think I could be an astronomer, and I wanted to respect my family's wishes. So I did go to a large university like this one. I took all the sciences, and after I'm like, I'm just going to try to be an astronomer. But because, you know, when you're an undergrad, I hope they're telling you if you're studying physics or chemistry, you're going to get a job. Like, it might not be as an astronomer or physicist, but you'll be well-trained and you can get a job. So I didn't worry that I could study to be an astronomer and it might not work out, because I knew if I couldn't be an astronomer, I'd be trained, like today you get trained in data science, there's a lot of things you can do. So I decided I would just go for it. And what really helped, which there are opportunities here too, is to get like a summer job. It's not a super high-paying job, but a job working in research to see if you like it. And I think that would be really the next step. And that was my path.
All right. Thank you, everyone, for coming.
Okay. Thank you.